Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week. And we're going to talk a little bit about something called the boundary layer and how you can use the temperature or the difference between the temperature and the dew point to estimate the base of the clouds. It's not an exact calculation, but at least it gives you a rough ballpark. And this only works with low-level clouds and low-level clouds that are induced by surface heating, okay? If you have a situation where it's rainy and cold and there's an inversion, this isn't going to work with that, okay? But if you have a type of situation where it starts off sunny and then you start to develop cumulus clouds that are produced by the heating of the ground and then the heating of the air above it, then you can make a reasonable estimate or at least get a ballpark idea as to what the base of those clouds are, the height of the base of those clouds. So let's go on ahead and get started here. And this is the visible satellite loop from today. And you can see that we started off perfectly clear, and then with the heat of the day, we started to produce these stratocumulus clouds in here. And actually in some areas, especially north of the triangle, it actually reached a point where there were more clouds than sun out there, but there was still some sun leaking through for sure. So here are some interesting things to know. The sun does not heat the air directly, okay? What happens is the sun heats the ground, which then heats the air above it by conduction, and then, or which is another word for contact, and then these air parcels that are beginning to rise become buoyant and transport heat upward to higher and higher levels through the process of convection. And convection is simply a fancy word for the process that leads to thunderstorms, where air parcels become buoyant. Buoyancy is a force. Forces cause acceleration, and you have upward motion of this air parcel that accelerates upward, and it keeps accelerating upward until it reaches a point where it is no longer warmer than the environment that it's in. Once that equilibrium is reached, then the net force is zero, the acceleration stops, and things begin to slow down. Okay, so the vertical extent to which this process extends defines what we call the boundary layer, which basically is the layer of the atmosphere that is influenced by the ground, okay? Once you reach the point where the ground is no longer having any influence at all on the atmosphere, then you are above the boundary layer at that point in time. And within the boundary layer, we say that the air is well mixed, okay? That's simply a term in meteorology. So, some more things to know. The temperature elapse rate in a well-mixed layer is about, not exactly, but about 5.4 degrees per 1,000 feet. So the temperature of the air would decrease every 1,000 feet that you go up about 5.4 degrees. The dew point, which is the temperature at which you have to cool the air to reach saturation, the elapse rate in a well-mixed layer for the dew point is about 1 degree per 1,000 feet, okay? So, for every 1,000 feet, the temperature and the dew point are getting 4.4 degrees Fahrenheit closer to each other. So, let's take an example here. Let's say the temperature at RDU is 47 and the dew point is 25. Well, let's start subtracting 5.4 from the temperature and 1 degree from the dew point over and over again until those two numbers meet. So, at 1,000 feet, the temperature would be 41.6 and the dew point would be 24. At 2,000 feet, the temperature would be 36.2 and the dew point would be 23. At 3,000 feet, 30.8 and 22. At 4,000 feet, the temperature would be 25.4 and the dew point would be 21. And finally, at 5,000 feet, the temperature would be 20 and the dew point would be 20 and the air becomes saturated and the clouds begin to form. So let's test this formulation, if you will, with a couple of places in North Carolina this afternoon. Now, these observations were taken at 3 o'clock. Now, at RDU, the temperature at 3 o'clock was 60 and the dew point was 31 and the temperature dew point difference was 29. So if we know that the temperature and the dew point get 4.4 degrees closer per 1,000 feet, you divide 29 by 4.4 and you get, 6.59, and then you have to multiply that times 1,000, okay, to get the actual height. And so 6,590 feet would be your estimated base, and the observed base at RDU at 3 o'clock was 6,500 feet. That's pretty darn close. At Greensboro, the temperature was 58 and the dew point was 29. They also had a 29-degree difference, so their estimated base would also be 6,590 feet. But at the Greensboro airport, it actually only reported a cloud base of 6,000. But that's still only 590 feet different. So again, it's not an exact calculation, but at least it gives you some ballpark. And if you're driving around and you look up at the clouds and you say, I wonder how high up those buggers are, then this gives you some ballpark idea. If you know the temperature and the dew point, give you some idea as to how high those clouds are. But again, this only works for surface heating induced clouds. It won't work on a cold, rainy day or really any sort of a stable atmosphere. It always has to be these convective clouds that either grow into thunderstorms or just turn into, like what we saw today, stratocumulus clouds that then spread out across the sky underneath an inversion, which is the top of the boundary layer. Okay, I hope that makes a little bit of sense and you find it at least mildly interesting. That is the bonus weather video for this Friday. Again, as I mentioned earlier, I will be leaving here early Sunday morning to drive to Ohio. And I am hopeful that I will be able to see the total solar eclipse up there and take some pictures. I have been educated on how to do that. And so I hope to be able to get those pictures taken and shared with you before Monday is out. In the meantime, you have a wonderful Friday evening, an even better weekend, and we'll talk to you again on Monday from the Midwest. Take care, everybody.